Let me start by thanking organizers of this very nice workshop and giving me opportunity to present this work here. And today I'm going to talk about spin galvanic effects in layered van der Waals systems. And towards the end of my talk, I will also discuss over very exciting recent results about magnetization manipulation in all van der Waals systems. But before I jump into this topic, I just want to everyone knows that why we are so excited about 2D material as a platform for probing spin and magnetism related phenomena for spintronics applications. Now, since the start of this 2D field with the discovery of graphene, we knew that graphene is an excellent spin channel material, particularly because you have long spin coherence in terms of spin lifetime and spin diffusion length. Then we came across this transition matter dihalogenide, where you have giant spin splitting, spin valley locking, strong spin orbit coupling, which allowed us to probe optical excitation of spin polarized carriers in these materials, right? And also, over the last couple of years, there has been very exciting development about experimental realization of long-range magnetic order in thin flakes of van der Waals materials, particularly chromium triiodide, chromium trichloride, CGT, FGT, and then what this allows us to is to probe spin or magnetism-related phenomena in atomically thin materials. And on top of that, what we can do now is we can combine these materials together. We can take one 2D material combined with another 2D material, and we can tune optical, electrical, or spin-related properties. So in nutshell, what we have is a really comprehensive 2D material toolbox, which is available for spintronics. So it's like a very exciting time in the field of 2D and also spins and magnetism. Now, coming back to the topic of this talk, which is about spin charge interconversion in van der Waals system. I'm going to talk about is a system of conventional heavy metal and 2D material, which is graphene, and then we make this interface using van der Waals method. And actually this work was done when I was a postdoc at Ohio State University in groups of Chris Hamel and Roland Kawakami. And the motivation behind this work is, we know that for spin charge interconversion phenomena, interface plays a very important role, right? And we have actually seen in context of these 2D materials over the last couple of years, we have seen very nice works coming from different groups across the globe, where we saw that if you take two different two-dimensional materials, mostly graphene and TMDs, if you combine them, then there can be emergence of novel spin galvanic effects, including a Rashba Edelstein effect or so on, right? So it is really important to control the interface quality and then transparency of this interfaces, right? So now when we talk about spin charge interconversion, right? So we are talking about how to generate or how to detect spin currents, right? And for that, we have different experimental techniques at hand, including a widely used method of electrical spin injection, where what you do is you take a ferromagnet, you apply a charge current from ferromagnet to a non-magnetic material, and you can generate a spin polarized electrons. Also, you can employ a magnetization dynamic space spin pumping method, where you use precession of a ferromagnet to transfer angular momentum from a magnetic system to a non-magnetic material. And we have also a technique based on optics, where you can use circularly polarized light to optically orient charge carrier spins in a semiconductor. And particularly in context of 2D, this is what has been done for transition metal dihalogenide. And on top of that, what you have is you have also you can also generate or detect spin currents in a non-magnetic material through spin galvanic effects, including a spin Hall effect or Rashba Edelstein effect. So my work mostly will be focusing on this aspect of detection and generation of spins, where we want to use a non-magnetic material for spin charge interconversion. And as I said, what we're going to do is we're going to take a well-studied system, well-studied non-magnetic system, which exhibits a spin Hall effect or spin due to spin orbit coupling, and then couple it to another, a two-dimensional material. In this case, it's going to be a graphene, a fuel graphene. And as I said, because interface is really important, and then from our previous experiences, we know that it's very hard to grow something on graphene. If you want to grow some material on graphene, whether it's magnetic or oxide or non-magnetic materials, you always end up getting a very rough interface, and which can adversely affect this spin charge interconversion or transparency of spins across this interface. So to overcome, what we want to do was like control this interface, and then the way we want to control that interface was like using inverted van der Waals heterostructure. Meaning, what we do is we first make these nanowires of platinum, and then deposit this fuel graphene, bilayer or trilayer graphene on top of these flakes. And then what we do is then we define these ferromagnetic electrodes, which I'm going to talk about later, which we will be using for injection or detection of these spin currents, which we generate or detect at this platinum graphene interfaces. Now, if you look at the topography of this interface, particularly platinum graphene interfaces here, it's very clean in the sense that it's free of any wrinkles, it's free of any contaminants or bubbles which are coming, which can come through when we make this heterostructure. So which is great, right? Now, once we have these devices, first thing we want to do is we want to make sure, we want to characterize what is the spin properties of this graphene channel, so that we can later on we can work the numbers and see what kind of efficiency we are getting in this platinum graphene interfaces. And for that, what we do is we do standard non-local spin transport and spin precession measurements with using two ferromagnetic electrodes. For example, I can choose any of these two electrodes. Particularly, we choose electrode which is near to this platinum electrode, which we are going to use later on in experiments. And we use E1 and say E2, we apply current and then measure a non-local voltage signal, and then we see a clear signature of MR, which is which tells you that you have spin transport, non-local spin transport in graphene. Then you can also do is you can also apply some transverse magnetic field to process the spins to get information about what is a spin diffusion length in graphene, what is a spin relaxation time in graphene, and what is also the ferromagnetic electrode spin polarization of your injector and detector. So once we have this thing out of the way, then next thing we want to move on to is try to experimentally show the spin charge interconversion at this platinum graphene interfaces. Now, if very naively thinking, right, because we have platinum, which is a heavy metal, that means if I apply charge current through it, what's going to happen is because of spin Hall effect, you are going to induce spin currents on top and bottom interfaces, and then spin polarization depends on the direction of applied charge current. And then if I apply charge current, say along y-axis, I'm going to get spin polarization along with plus minus x direction, and this spins can decay, diffuse into graphene, and then they can be picked up, they can be detected by another ferromagnetic electrode. So this is first we're going to focus on we are focusing on the spin generation at platinum graphene interface. So this is how we do measurements. What we do is we apply a charge current here, and then we want to use a ferromagnetic electrode whose properties we know, and then also graphene channel, which we now understand in terms of what's the spin diffusion length and what's the spin relaxation time and so on. And then we want to measure this non-local voltage signal as a function of applied magnetic field. Now, initially, because of the shape and isotropy of your this ferromagnetic electrode, your magnetization is pointing along y direction, which is normal transverse to the direction of your spins that are being generated at this platinum graphene interface. And what we can do is we can change the magnetization direction of this ferromagnetic detector by applying an external magnetic field. And what I want to do is I want to change the magnetic field, change the magnetization, and then look at this non-local signal. And then you see that we see very nice increase in the signal, and then it saturates as expected when the magnetization is along the direction of your injected spins at the platinum graphene interface. Right? Obviously, you can also apply magnetic field in other direction, and then you will see a nice reversal, opposite polarity for opposite applied magnetic field. Now we can, if this is coming from some spin galvanic fact, say spin Hall fact or so, we can reverse the polarization of the spins which are coming into graphene by reversing the by applying, say, negative current, right? So this is what we do, and then this is clearly we see that if we switch from 10 microamp to minus 10 microamp, we clearly see a reversal of this this signal, this spin charge conversion signal. Now this tells you that basically we can achieve charge to spin conversion in the sense that we are applying charge current at the platinum graphene interfaces, and then it is converting into spins that we are detecting using a ferromagnetic electrode. Now, what we want to do is, now we want to, if you want to look at the unstaggered reciprocity, we also want to see what happens if we send spin currents at this interface, platinum graphene interface, right? And one of the things you can think about is you can send spin currents with different spin polarization using this ferromagnetic electrode. And then spin polarization of injected spin current is defined by the magnetization direction of your ferromagnetic electrode that I can control by external applied magnetic field. Now, if I send spin currents, if I put my lead this way, that along plus minus y direction, and if my spin polarization is along plus minus x direction, then what I'm going to do is I'm going to pick up some non-zero voltage. But if I send spin polarization along y direction, and then I should expect some zero signal, because it doesn't, if you look at the cross product, how we inverse spin Hall fact works in platinum, you're not going to pick up any signal. You're not going to generate any applicable electric field in this geometry, right? So this is exactly what we observe. What we do is we use this same electrode, right? So now we are using this ferromagnetic electrode to generate spin currents in graphene, and we want to study these spin currents at this interface. So as expected, when phi is 90, when magnetization, when I apply a magnetic field along y direction, and then the magnetization of ferromagnetic electrode remains along y direction for a small field and large field because of shape anisotropy. And what happens is I get zero signal. But then what I can do is I can pick up some other angle, say if I apply along zero direction or 180 direction, which is transverse to this y direction where you're doing detection, and then I see nice signal increase, and then it's saturated, because it depends on what kind of spin polarization you are sending to generating through this ferromagnetic electrode. Now what you can do is you can do this, you can look at the magnitude of this signal, right? Magnitude of between, you can pick up either a blue curve or red curve, and then you can see that, oh, what's the magnitude from highest and lowest, values of this voltage measured. And then I can plot that as a function of field applied in different directions, and then we see a nice cosine-like behavior of this signal which is being detected at platinum graphene interface. So Now, this basically show you that we can achieve both spin to charge conversion and vice versa, as I shown before, right? So one of the interesting thing that we observe in this heterostructure is that the magnitude of this spin charge interconversion signals is actually order of magnitude larger than what people have previously reported on platinum graphene interfaces. The only difference was that in previous works, what they have done was they had to graphene and then put a platinum, directly deposited platinum on top of it. The only difference we are doing here is we are just trying to control the interface, trying to make sure that interface is clean, right? Now, you can also look at how this depends on the other parameters. For example, how it depends on the applied charge current, how it depends on gate voltage and temperature. And mostly we see a very, as expected, we see it linearly, the voltage signal linearly increase as a function of applied charge current at the platinum graphene interfaces, and gate voltage shows very weak dependence as well as temperature dependence, right? Now, so then question becomes, okay, so what we observe is it's signals, we just invert the heterostructures, and the signals are order of magnitude what has been reported before, right? So to quantitatively understand this thing, we can look at the one dimension diffusion model for spin transport in platinum graphene ferromagnetic non-local spin Waals, where we take into account for electrical spin injection with ferromagnetic electrode, spin detection with platinum electrode via inverse spin Hall effect, or vice versa, and how spins diffuse into graphene. And then actually this was done. This modeling was done by Jianzheng Yu, and one of the things we right away find out is if we compare it to very nice work which was done in the groups of Felix Casanova and Sergio Valenzuela, where they have used platinum to inject and detect spin currents in graphene. As I said, the only difference is they are evaporating platinum on top of it. And if we compare these results to these groups, one of the things we see is obviously our signals are large, and then to explain that signals, we need unphysical spin Hall angle in platinum reaching 500%, which is kind of, which tells us that maybe just a lone spin Hall effect cannot explain our large spin charge interconversion signals, and perhaps something more going on in these systems, and perhaps maybe something called Rashba effect, right, at this platinum graphene interfaces, right? So let me briefly mention what's the Rashba effect, right? If you have any two-dimensional system, either due to crystal symmetry or broken inversion symmetry at the interfaces, it can lead to a special kind of it can lift the spin degeneracy of the bands, and these bands in this kind of system, they have spin textures, particularly something called spin helicity or spin momentum locking, where your in-plane spin polarization is oriented transferred to the momentum of the electrons. And this has been probed in a number of systems, including graphene TMDs and also conventional oxides systems, and also in topological insulator. The only difference is you have only one, spin momentum locked Fermi counters, right? And we know that in this kind of system, Rashba system, through this Rashba Edelstein effect, what can happen is if you apply a electric field on this kind of system, what happens is you can generate some imbalance of spin up and spin down charge carriers in terms that you have generated a non-zero net spin polarization. And if this is true, right, this is if you apply current and you can convert it to spin, the reciprocal process must be true, that if I send a spin current on this kind of interfaces, it should also generate some electric field. And this is, well, as I said, has been a focus of recently a lot of studies in 2D as well as in oxide systems. Now the question is, okay, why I'm talking about this, Rashba effect in this platinum graphene? Actually, it turns out that there has been studies, angle result photoemission studies of graphene on gold and platinum, and they have seen that, if you put a graphene on gold or either platinum, what you can do is you can end up splitting the spin up and spin down bands due to this spin-off decoupling, Rashba induced spin-off decoupling, and these actually splitting can be as large as hundreds of milli-electron volt. And what we think is going on in this heterostructure is that in our heterostructure is that we have graphene where you have spin degenerate drag dispersion of graphene. But when you couple it to a graphene, the pi orbitals of graphene hybridize very effectively with the 5D orbitals of platinum, resulting in this spin splitting of graphene and forming some kind of Rashba interfaces, which can contribute to enhanced spin charge convergence signals that we have seen over heterostructures. So to summarize this part, I want to say that just taking a conventional system, well-studied system, and controlling the interface, you can achieve large spin charge interconvergence in two-dimensional systems. And then spin Hall fact, at least in our case, cannot fully explain our large observed experiments. And it points to maybe perhaps there is more going on than just simple spin Hall fact, spin charge interconversion due to platinum. Now, in last couple of minutes, let me share very exciting result that we have been working recently on. It's about spin orbit torque switching in all van der Waals systems. Now, if you look at a spin orbit torque switching, normally it involves heavy metal or heavy system, and also some magnetic system. And what you want to do is you want to use spin currents generated in this material, which puts spin orbit torque on this magnetic system to efficiently manipulate the magnetic state of this layer. Now, there has been a lot of work people are trying to do where they are trying to couple 3D heavy system, for example, platinum with van der Waals magnetic system. We heard very nice talk from Professor Yingshi yesterday, where they are using platinum to control the switch the magnetization of FGT. And also there's very other nice work where they did the same work. And you can also think of that there's you can use van der Waals heavy system, for example, WTE2, which has large spin Hall angle or surface states that can be used to manipulate the magnetization of a 3D, a 3D magnet, particularly in this case, permalloy. And one of the thing which is missing in this so far in this field is how can we achieve efficient switching of a magnetic systems and using a van der Waals magnetic system and using a van der Waals current source material, right? So for that, what we do is we focus our attention on WT2, which has shown to be excellent material for generating spin currents out of all these 2D materials that we have at hand. And for ferromagnetic material, we use a FGT, which has perpendicular magnetic anisotropy. This is one of the flags which we use for these devices. And we make this heterostructure where we have this platinum. We choose FGT thickness around 40 nanometer to compare it to existing studies where people use platinum to switch magnetization of this FGT, and then we use 20 to 30 nanometer of WT2. And this is the characterization of magnetization characterization in terms of anomalous Hall of FGT films as a function of temperature. And you can see that we see a very nice square loops, and then Curie temperature is around 220, 230 Kelvin as expected from other studies also. So here's the main results where I'm showing you SOT switching of FGT at 190 Kelvin. This is the square loop, anomalous Hall square loop at this temperature, and then in presence of some bias field, we can switch the magnetization from up and down states. And then obviously chirality changes if we change the bias field, right? And then one other thing you will see that it's not switching between full. This is normalized with the anomalous Hall resistance, but I think our devices are not perfect Hall bar. That's why we are not able to achieve full switching, but definitely we can switch between top and bottom states. Now, one of the thing we want to look was like, okay, is it more efficient or how is compared to other materials like platinum if we use platinum? And this is the graph showing that where we have extracted threshold charge current density required to achieve spin over torque switching of FGT of similar films, right? In this work, they used 30 nanometer. This is Professor Yingshi's work. They used 50 nanometer, and then you can clearly see that over at least, if not better, it's definitely or the same order of threshold charge current density, which is required using this all van der Waals bilayers. So to summarize, what we have shown is that we can switch the magnetization of a 2D magnet layer using spin currents originating from a van der Waals material. And then, as I said, switching efficiency looks better as compared to conventional heavy metals. And this is the first step towards all 2D metal memory devices. And these are the students who worked on this project along with my colleague and then collaborators who provided samples for this work. And with that, thank you.